Let's build a Monte Carlo model together in Python to predict the possible trajectories of a retirement portfolio. Imagine it's your first week of retirement. You finally have the time, the freedom, and the feeling of relaxation, but your life expenses keep happening like clockwork. Grocery, trips, rent, insurance, all the normal stuff. Meanwhile, the market does what it always has, bouncing around with good years and bad years in a random order. The only thing that matters is whether your portfolio can handle withdrawals while those ups and downs play out. That's why looking at one average forecast might feel comforting but misses the real risk. And that's where Monte Carlo comes in. You can think of Monte Carlo as replaying the same situation thousands of times with variation to see the range of outcomes. So let's build a model to predict your portfolio after retirement. This model is based on the idea that Monte Carlo is not a clean, straight math problem. People love to say that the model returns 7% per year, but that's not how the real world works. Real returns bounce around. Some years are great, other years are awful, and you don't get to choose the order. So the key concept here is sequence of returns risk, which just means that the order of your annual returns really matters a lot. Two people can have the same average return over 30 years and still have completely different outcomes. If the bad years happen early, then those withdrawals will do way more damage because you're taking money out while the portfolio is already down. And that shrinks the base that future gains can compound on. And if the good years happen first, it's the opposite. The portfolio grows a lot and the withdrawals are easy to support later on. Now, to build this model, we're turning a simple retirement plan into a year-by-year story. You start the model with inputs like your beginning balance, your annual spending amount, and how many years you need this money to last. Then you decide how your spending changes over time, and most realistic models change their spending amount with inflation. So if inflation is 2%, you might spend $40,000 in year 1, and then a bit more in year 2, and even more in year 3. Next, we need a simple model for what a year in the market looks like. And to simulate this, we need a way to generate a realistic looking market return for every single year in the future. Instead of guessing exactly what each next year will be, you describe the market with two adjustable knobs. The first knob is expected return, meaning the average yearly growth you'd expect over the long run. The second knob is volatility, which measures how much returns typically sway and vary. High volatility means the same average return can come out with much bigger good years and also much bigger bad years, and vice versa for lower volatility. But once we've chosen these two knobs, we still need a rule for how to randomly draw yearly returns, and that rule is called a distribution. A common teaching choice is the normal distribution because it's simple and matches the idea of returns clustering around the average. The problem is that a normal distribution can generate returns below -100%, which would imply that our portfolio loses more than everything in just 1 year. That's not realistic for a basic buy and hold portfolio, since the worst case scenario would be losing 100% of all our assets and hitting zero. A more realistic beginner alternative is the log normal style approach, where you generate a positive growth factor for each year and convert it into a return. Because that growth factor cannot go below zero, it automatically prevents any impossible returns. And this is the simulation itself, where it's just repeating the same yearly update but with a different random return path each time. For one simulated future, you draw the return for year 1, update the portfolio, subtract the expenses, and then keep going for year 2 and year 3. At any point, if the balance hits zero, then that path is marked as a failure. That doesn't mean the person will die financially or go bankrupt in reality. It just means that that plan fails for the rules that you set. In real life, they'd adapt by cutting spending, working part-time, or delaying retirement. The model is intentionally strict so you can model the risk very clearly. You run the simulation thousands of times because, of course, a single path is basically meaningless. After 10,000 simulations, you can compute the fraction of paths that survive the whole way through. That becomes your estimated probability of success under these assumptions that you've set. And in real life, withdrawals and market changes happen all the time, but we're simplifying it into a year-by-year step to keep the idea clear. Now that we've finally run the simulation, we can actually interpret the results. We ran 10,000 simulations, meaning 10,000 different market histories, all starting with the same plan. Then we ask the same question: did you make it 30 full market years before hitting rock bottom? The answer here is that only about 13.2% of all our simulations made it, and the other 86.8% hit zero sometime over the 30 years, which is a huge red flag that this plan is too tight under our assumptions. The really important part is where these failures actually happen, because it tells you what the risky zone looks like. Among all the simulated futures that failed, the median ruin year is 15, meaning half of all the failed futures ran out by year 15. And most of the failures happened between years 13 and 20. Now, the ending balance percentiles might look a little weird at first because because all of them are 0, but when you see that the 50th percentile and even the 75th percentile are 0, that's just saying that a lot of the time the portfolios are drained by year 30. But then look at the top end. In the top 10% of scenarios, you still have about 336K left. And of course, this is just a model, not a prophecy. Real returns have unstable inflation, taxes, fees, etc. But the reason Monte Carlo is so valuable is that it forces you to stop trusting a single average. It makes you think in terms of risk analysis. How often do we survive? How bad are the worst cases, and how much buffer do we really have? And that is a full Monte Carlo for you, coded out to predict someone's retirement portfolio. So don't forget to save this video for your next Monte Carlo project and follow for more. See you in the next one.